All right, 7 o'clock. Let's get started. Today it's a review on lecture 6, uh, higher order functions. So actually, higher order function in some way you see there are lots of the examples in there that are simplifying the way that we needed to code with some kind of template. Because the template, in some way, you tested it for one example in a way, and then you can use it in many other instances. They're all similar. All right. So higher order function, it's a feature in Python. Higher order function in the sense that it can take function as input and also can output functions for use by other people, for use by other routines. All right. So this is so in a way, Python is treating the higher order function as first class object. By first class object, meaning that it is the same as uh, other objects like numbers, string, list, tuples, modules, and so on. You can actually dynamically create or destroy them or store them in data structures or pass them as argument to other function and use them as return values and so forth. I draw my uh, material from this web page. You should take a look at it. This is inert function. Actually, inert function, because of inert function, you can actually return the inert functions, and as a result, you are outputting the function. So there are some other examples in here that could be interesting to take a look yourself. Okay. Now, for us, I should emphasize the fact that even though it is allowed in Python that you can have function as inputs and function as output, it doesn't mean that Python is more superior than the other languages, like commonly known like Java, C, C++, etc., etc. All right. All the languages, computer languages designed are such that you have a way to do certain thing. It's just how convenient that way is for your purpose. All right. There are languages designed to fit, example like matrices in engineering. You deal with a lot of matrices, and they are languages that fit for that purpose, and you can maybe write in 2 or 3 sentences, you can get things done you can get the program behave the way that you want. On the other hand, if you switch to another language, maybe you need to have a longer program. That's about all. It doesn't mean that in here, Python is more powerful. It is the same as any other languages. Should there be a computational problem that other languages cannot perform, then it's the same going to be the case for Python, all right? Because there are certain limit in the way that computation can do, like you hear about decidable versus undecidable, maybe a few weeks ago. And when you apply to one language, it also apply to all the other languages, as far as we live in this world is. Okay. So now, but Python allows it. So why does it allow? Once it allows it, then it open up a lot of possibilities. Okay. And we're going to take look at them. That you can actually just now that web page that I told you, you can see them more comprehensively here. But allow me to just draw a few important points to illustrate. Then you can hopefully know why there are certain things being done and why certain thing it's difficult. All right. So as always, when a particular feature, in this case, this feature about higher order function, it's it's created, it serves certain purpose. All right. Or it serves certain convenience. In particular for us, in this case, is encapsulation. Encapsulation is similar to what you, for example, when we take medication, our drugs, it's put into the capsule. because the drug, it could be composition is a little bit bitter. We don't want to taste the bitterness. And we take the capsule, which is a the capsule that you will just swallow it without touching the inside ingredient, and you just let it be in your stomach that to digest it without your mouth or your tongue to feel the bitterness. All right, it's the same in this allowing this higher order function or inert function. Okay, all right, inert function, it allow you to actually encapsulate some of the thing that you do not want the outside world to know. You just wanted the outside world to see a particular function. Here, let me give you an example. This is the example from your notes. Okay, this is the coin change. All right, the coin change example is that you want to count the coin change. That is the main routine that you have. You want to count the coin change of certain amount. So, for example, we want to count change of the amount of 30 cents. We used to do $1, which is 100, but 30 cents is good enough for our purpose here, as you will see. All right, and so you want to do count change of 30 cents. You want to use 1 cent, 5 cent, 10 cent, 20 cent, 50 cent. Of course, 50 cents is useless because it's much larger than 30 already. So this is not going to be used anyway. So when you do count change, you're actually calling this routine. You pass 30 into here. And this routine actually needed to call another routine called CC. All right, just change it to an amount, which is 30. And there are 5 coins to use. All right, 1, 5, 10, 20, 50. And this CC, it's then called if the amount is 0, meaning that you don't need to change any amount, then you have only one way, that is use no coins. Okay. On the other hand, if the amount is less than 0, which is possible because you see that as part of it is to take the amount, subtract away some amount. So this could be a negative value after the subtraction. So you check if the subtraction is the amount is less than 0, and the kind of coins that you have for changing no longer and you don't have anyone, because why? You can see that the kind of coins can be subtracted with 1. So you started out with 5. You may decrease it to 4, 3, 2, 1, then 0. All right. Once you reach 0, or when the amount is less than 0, which is negative, then you have no ways to perform any change. All right. So you return 0. Otherwise, then this is the inclusion and exclusion. You can either keep the amount, right? Use one less coin. That is, you don't use one particular coin, okay? Or you take that coin and use it. The kind of coins in this case, it started with 5. You use all the 5 coins. You take that denomination, that coin, take it away, and then you continue your counting of how many ways of using to change the coin. So this is to exclude a particular coin. This is to include that particular coin, but you must exclude that amount. Okay. So the sum of this with this then give you the actual count of number of ways. One is to use, for example, 1 cent. The other one is not to use one is not to use 1 cent. The other one is to use 1 cent, and go ahead and use 1 cent. Okay, so there's no overcount and no undercount. By itself, it's undercount, but summing the two is exactly no overcount and no undercount. All right, so this is the answer. So let's run it. All right, you have the 20 ways to do it. Okay, so this is the coin change routine. So now I want to show you how we can encapsulate it. Now you see this coin change, this count change is the only thing that you needed. You don't need CC is supposed to be hidden. So what we can do is that take this, or you take this, all right, to hide it within here. Okay, this become an inert function. I must indent it. All right, I still should get the correct answer. Let's run it and see how. Now you see, I still get 20. In this case, what good does it do to us? Now CC is no longer available. So if you try to find CC, is a function because just now it's still here. So I should delete it here. I should remove it. Then I run it. Okay, I still have 20. Now if I try CC, it no longer exists to the outside world. Okay, now there's one more function that I want to get rid of, which is this guy. This guy is a reference in here, okay, and no one else needed to know it. So I should just take him and make him into also an inert function. All right, I still get 20, and now I have encapsulated this function and this function within the coin chain. And no one else outside of this count change needed to know about first denomination on this. For example, now if I change this to 10 and change this to 5, it doesn't matter. The answer still remains the same. Okay. Likewise, if I change to another, if I get rid of this guy, I don't need him. Or I put my 20 in front and my 1 at the back. It's still no difference. But you have seen that the efficiency may be different, but in terms of the answer, it's still the same. Okay, so this is encapsulation. I have encapsulated first denomination and CC within count change. All right, so this is allowing with the use of this, it's to allow you to do that. All right, this is an opportunity for me to show you something what we call in the recursion. So I digress a little bit. Allow me to digress and show you this interesting feature. Now you see that when I do recursion, I actually needed a terminating condition, which means this is my terminating condition, which doesn't do any basically base case. This is our base cases. All right. Okay. And this is one. Secondly, I must have a smaller problems. All right, smaller problems. This is my smaller problem. This is smaller problem because kind of coins is subtracted by one. There are two parameters. I minus one means I have less coins, so this is a smaller problem. And this one, calling CC, also a smaller problem because in calling CC, I'm using the amount subtract away this denomination. Okay, even though I keep the kind of coin change is remains the same. All right, so you always have smaller problem to solve, and you always have terminating condition. An interesting thing in recursion is that I can carry baggage, all right, from one level into the level. So here is the use case. The use case here is that, okay, I know that there are 20 ways to do it, but how does it look like that 20 ways? Can you show me that 20 ways? All right, so that's what I'm going to change this program to show you the 20 ways. All right, how does it look like? First of all, uh, I do this count change, right? 30. So I call in here 30. I do not want to change this. I will just CC amount 5. So this is the 5 ways. I wanted to add my baggage here. This is my baggage. Initially, my baggage is empty. Along the way, I will accumulate the baggage to know what I have performed, what I have used, what kind of coins I have used. And then I will output that at the end of it. Where do I output it? Surely it's here. When the amount exactly equal to 0, this is where I should output what I have collected all along. Okay, so it should be print whatever baggage I have here. Okay. But I forgot here, this is my baggage. Let me put it in because now I have three parameters: amount, number of coins, and my baggage. All right. Amount, number of coins, and my baggage. So this is the place that I print out the baggages or the baggage that I've collected and output it here. All right. This is when I have finished or changing my amount. Now here is returning zero. So it means that this is not a possible case. So there's no way that this case you can just ignore it. So the baggage collected all the while until here, you can just simply ignore it and return zero. Okay. The next thing that the baggage come into place is that amount and kind of coins. So if you keep the amount and you don't change you reduce one coin, then the baggage has no change. Okay, meaning that you didn't do anything with the baggage collected so far. You just reduce the kind of coins by one. Then where is the place that you needed to change? Here it's where you needed to change. Here is when you actually use this particular coin because you subtract it away from this amount. All right, so the baggage here is then changed. I edit my baggage. My baggage is whatever collected so far plus a space to segregate it from the other, and then I make a string of my first denomination kinds
Back.
of, sorry.
Head people to side.
Hello, Samuel, can you off your mic? Yes. All right, so this is what happened. I use this coin to make the change, so I subtract the amount away. So I added this denomination into my baggage. All right, I make it into a string before I add it. And that's all I needed to do to carry baggage from one level of the recursion to the next level. And I can see now that my answer, if I don't make any typo, see? So I have 20 ways. And what are these 20 ways? It looks like one 1 cent for 30 times, and then or you have 1 cent for 25 times and a 5 cent, or you have a 10 cent or 20 cent. Okay. Likewise, you can change this to $1. You will see actually just now maybe I would just make it into the more standard way. 1, 5, 10, 20, 50, and run it. This will be exactly like what you have in your lecture note. All right, 343 ways to change $1. And one way is 50 cent, 50 cent. Another way is 50 cent, 20 cent, 20 cent, 10 cent. Or much earlier, you have 100. Oh, it's a lot. So maybe we just change this back to 20 instead of 30. We'll see we get you the same. All right, so there are 10 ways to change 20 cent. Just one single 20 cent, or two 10 cents, or one 10 cent and one 5 cent, and two 5 cents, or 1 cent all the way, or one 5 cent and 15 1 cent, and so on. Okay, so this is the powerful thing about recursion. You accumulate each time you make a decision, you accumulate what you needed into your baggage. At the end of it, which is here, you print it out, and you indeed printed it out on three like that. That and up, and also you can get your answer because this is printing the answer, while here is printing the baggage for you to see. All right, so this is a very interesting, powerful thing. You should try this thing for your Tower of Hanoi. All right, it's the same. Tower of Hanoi needed you to move from peak A to peak B, peak A to peak C, and you can see how you can do it from A to B, B to C, and so on. All right, so you should try it. Okay, so that is encapsulation digression. I digress to show you something, which is a very important thing because most of the time people don't tell you this. People hardly tell you this, as far as I know. Whenever you study recursion, people tell you these two things, but actually there's a hidden talent or hidden power of recursion that you can capitalize by inserting baggage along the way. Okay, so the second point I wanted to point out about why we allow. All right, so you see in our lecture notes, okay, this is slide 33. In our lecture notes, in programming, actually, in general, actually you will see this in C, C++. Is indeed talking about template. Okay. Why this come about? Because you have standard a few some standard way of solving problem. I remember there is this the giant with object-oriented programming. You have a few patterns that you have to remember, or not remember, but you can refer to, and they solve the problem. Basically, they are designed, they're already there. You just make use of those designs. And basically, you're standing on the shoulder of the giant. They have done all these things for you before. Of course, we up to this level, we don't want to remember or by heart some of these things, but you should know that they exist. Okay, they exist that you can always Google it to find out. All right, here for our example is that you see that the sum and the product, these two routine, the structure looks the same. All right, you see, you checking a condition, you return a zero. You checking condition, you return a one. If not, then you return this thing plus this thing. Otherwise, here for the product is if not, you take this thing times this thing. All right, so all these are similar. At least these two structures are the same. You could actually write a common one for them and test that common one. Once you have tested the common one, you can use it for both of them. All right, by substituting the initial condition and the operator you want, which we are going to see today also here. All right, we are going to see the sum and the fold. The sum, it's a way to do things which is what you saw just now here. Is similar to this sum, and so this adds that we don't, in a way, we don't write new codes. We simply use the old one, and therefore, testing is not really needed in a way. As long as you can, confident you use the template, you can get what you want. All right, and we're going to see this in our recitation number 3 shortly at 8 o'clock. Okay, the next point I wanted to illustrate to you, it's this one. All right, repeat pattern. This is a code that you have seen before. Slide 40. Okay, so this is the repeat pattern. The code looks like this. We studied this previously, and I told you that you can write this thing differently, and also you can write this thing in a sequential manner. All right. So now this picture, which is a homework, if you really try it, is that repeat pattern. It's taking in 3 parameters to output one picture. Okay, so basically you transform this picture into this other picture based on what you want to do with creating the pattern and how many times you want to do it. Now, this particular routine could also actually be broken down into two so that you can create an intermediary function, this npad, and this npad you can choose your name. All right, for example, here Repeat pattern is a little bit harder to understand what it means. Only until you study, then you know, oh, it is trying to make cross. Pattern is a make cross on a particular picture how many times. Okay. On the other hand, if you can break it down into two routines, this is one of the two. This is repeat pattern is one of the two. Then it outputs this routine, and you can name this routine the way that you want it, so that when you subsequently you can use it with that names, and hopefully that it's a more meaningful name. Okay, as we will see. All right, let me just call it up. All right, so this is the routine. Let me comment out all these things that we don't need anymore. Okay, so this routine, let's run it. Oh, I forgot to uncomment. Okay, I forgot to uncomment this, but I can still use it. All right, you get this. Okay, so now I want to change this thing. I want to break this into two routine, like what I show you in the slide. Okay, in this slide, I want to break this routine into two. So how should I do that? So first thing, it's that, let me define. So the repeat routine, repeat pattern, it's now with two parameter. Okay. And I want to create this function to be returned by this guy. So I define the pattern, the name, okay, the picture. All right, you know that this npad is going to take this picture. And at the end of it, I want to return this npad. All right, so this npad is what I wanted to return. And I need to perform this thing sort of within the init function. So I need to create another one, another level, define helper, whatever you call it, doesn't matter. And with basically this it's going to help me to perform this kind of recursion. So I do that. If m equal to 0, I mean, basically you are returning the picture. All right, the picture here. Okay. Otherwise, you return the pattern, okay, which is this pattern, to apply on the helper one last time, and do that. Do I miss out something? M minus 1. Oh, yes. There shouldn't be a bracket here. Yeah. Okay. So this is the helper for me to the npad itself needed to do the recursion. All right. So this guy only take these two and output this function, which what we do. So there's no parameter here. Okay. And the actual routine to return is here. Return the helper, the n comma pad. All right. So let me explain this a little bit. So now you see that this n it's used here, and this pad is used here. These two things, it's then to call the helper function to perform the recursion, which is the same as here. All right. So this not much change from here. The only that we see is that instead of doing this directly, it does it with returning this function, which is doing this branch to give you this. Now, once this branch is outputted, this thing is outputted, what it does is that it can take in a picture, which is the picture here, all right, and then be used within this routine to help us to create the same pattern. Okay, let me comment out this and move this to below to see. But let's see, check a little bit. No problem. Okay. Oh, okay. All right. It's a little bit of problem. So this is true. I forgot to uh here. Okay, I cannot do this. Uh, repeat pattern is going to, this is a wrong thing. So what I have to do is that I want to give you the name, make cross 4 times with this routine, and this is what, now I created a function called make cross 4 times with, and then this is exactly this routine. This is gone. Okay. Then now I can show my make cross 4 times with a picture, and a particular picture. In this case, I want to use Nova DB. All right, so now I should be okay. Let's run it. Unmatch. Yeah. Okay, so it gives you the same result. But what do we gain here? We see that we now have this function which are more explicitly saying the intent of our program. All right, so basically npad here is actually called make cross 4 times with a particular picture. Okay, so you can also do this with the heart. Okay, for example, all right, here. All right, so there's a few other things I want to show you. Um, okay, first of all, uh, now you see that this guy is serving the same purpose as before. All right, so with the advantage that I can give you the name, and this name may be more meaningful, or you can be more clever than me in getting a name that more explicit. That's one. Number two, you see that actually this N and this pad, it's actually here and here. All right, so they are actually the environment. This N and pad, which is for and make cross, are the environments that given to repeat pattern, and they are kept with the helper. They are there in there to remember, basically, that you don't have to worry about it. Of course, this is also something maybe a little bit unusual for those of you who have prior programming background, and but this it's what Python is able to do. The next thing you see is that actually this n, if I change this to n, it doesn't matter to me. And all right. This here comes the scoping, which we will see afterward in recitation number 3 or so. This n is nothing to do with this n. That's one. But this n is the same as this n. Okay, so just now you saw that this is n, this is m, and m, it still work, right? Oh, did I change this n? Oh, let me, okay, I must have. Then the next thing you see is that this pad, all right, is pad here. I could have changed this to PAT, 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 And it may seem that this pad and this pad are the same. Actually, this is actually the value from here. So this guy and this guy are the same, but this is an parameter. This is an argument. This is an argument that passes into the parameter. All right. So this is by right different from this guy. All right. This is again the scoping. Using a same name as the one outer function, this is actually the scoping that this guy is here, but this guy is not here. Okay, this and this are different, but this and this are the same. All right, so let's see. Now I make it even more confusing, but it still work. You sure? All right, it's hard. I should change this to the Nova, which is more familiar to us. Okay, so it's just this. Right, so the scoping is kind of important, that you realize this n and this scan are different, this pad and this pad are different, but this n it's the environment, all right, that it's coming from here and it is being kept passed into this return. All right, okay. So this is the next note. All right, so this is a ease of reference in a way. We make a name, make cross 4 times with whatever. Okay, if you change this to 5, then this make cross 5 times and so on. All right, so it says that it allowed name convenience, as I demonstrated to you. Here's another example. Another example of powers. Okay, here is the power. Comment out this. So here is the power base raised to the power exponent. All right, so whenever you write this without looking at this base and this exponent, maybe this guy is a B, this guy is a E, then it is a B, this is a E. All right, and then or maybe even more bizarre with the B and the E. All right, so when you say power 2, 3, do you mean the 2 to the power of 3 or 3 to the power of 2? Okay. All right, so this power, you still need to refer back to the definition to see it and so on. So after that, you try it out, you see the answer is 8. Therefore, you know that this means power of 2 of 3. But you can make it even more explicit. Here is one way we do. Okay, I will do this. All right, generate power. Basically, I embed this guy into init function and I return power. I return this init function and I make it into a base. The base and the exponent separated from 2 parameters into 1, 1. Okay, then it becomes this. Now I can say this all right, raised to the power of 2 for something, generate 2. Okay, so I have this function. Next, if I print my raised to the power of 2, 4, of course this is verbose, but it's just to prove the point. 3. Okay, so raised to the power of 2, 4, 3, meaning what? So I will get raised power of 2, 4, 3 means I should get 9, right? I get 9. Let me comment out this 8. I get 9. Okay. So this is more explicit now. So that's what I meant by ease of reference. All right, same you can do All right, like raised to the power of 2 for 4. And if I want another one, raised to the power of 3, 3 of 3 for 4. So 4 to the power of 3. So this is 64. This is a power of is okay 2 for 4 is 16. All right, so I should get 9, 16, 64. All right, 9, 16, 64. Okay, so this is about ease of reference in a way. Of course, you must exercise this with caution. All right. So, like, you do not want what I've done here in a way that the function becomes such a long so part. Anyway, this is to show you that with the init function, I can do things that allow me to return the function and make it into something more explicit. After all, a program is written for other people to read. Okay, so all these things come with a price, like what we saw just now, that this n and this n are actually different. Okay, this pad and this pad are actually different because the scoping become a issue. So here is what you have to take note of. All right, the scoping of parameters. Just now you saw this x and this x are different. This x, whatever in here, it's in the function 1, not function 1. Okay. So you have to take note of that. And second one that this is yet another interesting thing that you have to you have to remember it by heart. This is a forgiveness attitude. So if a variable is not on the right-hand side in the function, it can be obtained from the global. Otherwise, one need to declare it in a global to be on the right-hand side to you. You need to declare under global. Okay. Global is a keyword on the right-hand side to user. We'll see this thing shortly. So this may look aliens to you, but it actually means something very straightforward. I will show you. Second thing that it come about is that you actually will be having a lot of lambda function. Okay. Lambda is a shorthand to write a function without giving the function a name. It looks like this. All right. This is a lambda expression. So lambda xy is a very shorthand. You have two parameters. You can add them. And so the output is this. This one line is the same as these two lines. All right, this no name is useless. You just anything you put here. Define no name x, y, which are the two parameters, and you return the sum of the two, x plus y. So you notice here that in lambda, in the way that you write lambda, there's no return. You cannot write a return here. Okay, if you write a return, there will be a syntax error. So that is should be straightforward. So you can say lambda xy equal to x plus y. Y. Oh, I cannot write this directly like this. I can say AA equal to, so can I say that? Lambda xy colon not equal colon x plus y. Okay, so just now I make a mistake here. It should be colon. Okay, so this is a lambda function. So if you try to put a return, you will get syntax error. All right, there's no such thing as return. This is another thing that you have to watch out. Lambda xy, if you want to do conditional statement, If x greater than y, you want to return x, else return y. You cannot write in this way. Number one, there shouldn't be any return. Number two, the if condition is not written in this manner. The if condition looks like this. You must write if within here. Then if this is true, the answer is here. And if this is false, the answer is at the back. So you see the statement looks like this, but there is no colon, no return, but it's different from what you used to write. If something return something else, something no, you don't write in this manner. In lambda function, you write the result if it is correct, otherwise another result. This is the same as this. Okay, so your condition is here. You return x. If this thing false, which is the else, you return y. Okay, so this is how you should write it. Okay, so this is lambda. We will see this again afterward. And let me see. Okay. There's another thing here that you should know. This one I give it to the other class, so I better give it to you. All right. This is a paper on 2020 midterm, only 2 marks. The paper has 30 whole marks, but 2 marks is a very little marks. And it looks like this. Define blur is like this, lambda. Define king is like this, return lambda. So the question asks you, what is blur king 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 for? What is the answer? King blur 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 for, what's the answer? Blur king, what's the answer? King blur, what's the answer? Just 2 points. So let's see. Dylan. Hello. Dylan, are you here? No. Yeah, your mic is on,
Yeah.
is it? Yeah.
Hello.
Yeah. So what is the answer for this guy?
The first one is
Hmm?
uh, wait,
Hmm? What? What's the answer?
is it 100?
Yeah, how come? Most of you get 100. Yesterday also 100 as the answer. Actually, no. The answer it's 2 marks. You're not supposed to use too much time. It's actually 16. Okay, why? Let's see, Blur. Blur is returning a lambda. It doesn't, this x and this x has nothing to do with each other. Remember just now we talked about it. This n and this n has nothing to do with each other. Okay? So whatever you pass to blur, x, I don't care. I only return you a function which will raise to the power of 2. So if you give me blur with king and king and king, I don't care. All these guys are ignored. They are ignored by blur. The blur only return you a lambda. So it's 4 raised to the power of 2, which is 16. Okay? Dylan.
Mm.
Okay, now next one. King.
Uh, 6.
Yes. Now you learn. Okay, answer is 6. Why? Because king is the same as the blur. It doesn't care about this x. It give you only this guy plus 2. So you give me blur, 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 also useless. Okay, you just take 4 and then plus 2. What about king blur, king blur? Blur king, blur king. What is this?
Uh, Also 16.
Yes, 16. Next one.
Um, Also 6.
Yes. Okay. All right. So that is what I meant by you have to be very careful. You have to syntactic. Syntax is correct, but semantic, you have to see the meaning of it. Okay. All right. So this is what happened. That's about all that I needed, and we have 10 more minutes. Let me just show you the last point. The last point is that we needed to, as you will see shortly, the recitation. You're going to do some, you're going to do full, all right, and some and full are some, actually, if you look carefully, some, without saying anything, some is a function. Or maybe I should restart this guy. Restart shell. Okay. Sum. Sum is a built-in function. This just now this sum is because of my sum here. Okay, so sum is a built-in function. So how does it do? It just take any number. All right, you just take a tuple, you will sum it up to give you the answer. All right, so sum is already defined. As you know in Python, we can always override the built-in stuff. So if I run this program, okay, now my sum is a function. If I do this, it doesn't work, huh? It doesn't work, because my sum is defined with a term A and the next and the B. So what I wanted to tell you is that as you will see in your recitation afterward, okay, all right, this sum, whatever we define is what you're supposed to use. You don't care about the system sum. Okay. So you just read whatever you are given. All right. This is because in some languages we don't have this kind of structure. As I say, Python support higher order function. So it allows us to quickly or easily manipulate or modify whatever is in the systems. So whenever you attempt our exercises or our assessment, you have to take note that whatever we give you is what you're supposed to use. You don't go and talk about the built-in function. All right. So after we will study this too, you can check out our midterm paper. You can see there are many ways of writing sum. Okay. We'll talk about them. All right. So the last notes that I have for you was to don't confuse with system version or whatever, huh? You just use whatever we give you. All right, and this is another point that I should make afterward about associativity. We'll see that. Okay, I'm done with my review on the higher order function. It's simplify the solution with template, actually allowing you to do things that to hide, to make it easy to write things or make it easy to refer to things. Okay, any question? If not, give me a check and we take a short break, 7 minutes. You okay? Otherwise, let's see. There's a chat. Somebody say something. As I don't understand, but is the pet function defined already in lectures 2 and 6? Oh, just now that routine, this pet is not defined. This pet is coming from make cross. Make cross replace the pet, the pattern. Okay. Same for PATT. It's this is the argument that pass into pet, which is the parameter. All right, so this is you see this is a function pass into another function to be used. Okay. So Rui Yang. Okay, if no other question, 6 more minutes, we take a break and I stop my recording and we come back shortly.
So sorry.
Yes.
That's a quick question. Can I ask, like, is counting change tested in the midterms?
Yeah, of course. Why?
Okay, because I like don't really understand the counting. It seems like a bit complex.
This
How
one?
they, yeah, the baggage part. Yeah.
Oh, the baggage part. Okay, baggage part, let me uncomment this
How
one.
does it generate like 10 plus 20 if it's not printing 10 and not printing 20? Like,
Okay, let's do this again.
sorry.
Uncomment. Okay, let me comment out all the rest. Okay, let's focus on this. Let's run. You see, there are 10 ways. Okay, maybe I should do number of ways. Okay, let's run this. Okay, number of ways is 10. Okay, how does this come about? If you want to really understand this, maybe you should try 5. Okay, how do I change 5 cents? I should be able to use 5 1 cents and 1 5 cent, right? So you see, run. Okay, you see, 5 1 cent and 5 cent. Now, how can you even know this? Of course, you can put this into Python tutor and you can see it. What you can do is also here. Oh, uh, I have to change the program. Baggage is equal to baggage is equal to O baggage plus space and then do this. Okay, first denomination kind of coin. All right, and I want to, then I cannot do this anymore. Oh, this is dangerous. Because this package is still the old package. So I should say this new package is the old package with this. Then I print O. So to understand code, you can always do this kind of stuff to print, to interrupt the code running with knowing what is happening. Okay, what am I doing here? I didn't touch anything here. I was just looking at my baggage. I will print it as a O, and when this CC this one go in, I will get a new baggage because it's a baggage plus this with this other thing. Okay, so let's see. Just use 5 cent to just check it out. You see, the O is nothing, the new is 50 cent. O is nothing, new is 20 cent. O is nothing, new is 10 cent. O is nothing, new is 5 cent. Okay, even with 5, it's already quite leceh already. O is nothing, new is 1. Here is something more meaningful now. So at some point, maybe you should print the amount also. Okay, to know that what are we talking about? Okay, see. So I'm all right. So the amount, when the amount is 5, the O has nothing. Amount is 5, the new is 50 cent. Of course, this new package will go in there, will get thrown out. The interesting one is this one. You now have 4 cent. Your O is 1. All right, meaning that you use up 1. And this case, this one is before I subtract about the new. So I should take amount minus the first denomination point. All right, you see that uh, if it's 5 minus 45, because you only have 5 cents, so you will try to use the 50 cent to change it. You are short of 45 cents. Okay, so nothing. Interesting one is here. You have 1 cent, you have 4 to change to 1 cent, you have 4 to change to. you have 3 cents, the amount, you have done the changes of 2 cents. 3 changes of 2 cents. Oh, why the same? I think, okay, you can discover this. I think we are reaching 8 o'clock. So what I'm saying is that if you have issue with my code, you can see that this accumulation is done with the baggage got added into the old baggage and go into the routine again. And at the end of it, he can then uh, collected it out. You see, he collected 4 of them and then he collected 5 of them. By the time he reaches 5, yeah, nothing else to change. So you can output this 5. And there's one other case is exactly 5 cents. Right, I think we cannot, I need to stop here and you can discover this with Python tutor also. Of course, Python tutor may not be able to run for big example, so you may have to be uh, careful with this number. If it's too big, it won't run. All right, so all in all, you just put in print statement to see what happened. But the interesting thing is that I only change 1 line, 2 lines, and change the function with 1 additional parameter. I get what I wanted. Okay, sorry, I have to stop here and start my recitation. Algebra, is that okay? Okay, thank you. All right, did I stop my recording? Okay, it's ongoing. Okay, good. So today it's recitation number 3. It's on higher order function, continuing from what we talked about just now to work with 2 functions. So here, the first thing to note is that in working with all this stuff, because you are going to pass function into a function, sometimes you wanted to write directly here the function. So we use things like lambda. Okay, lambda is a shorthand. It's a one-liner of your function. So let's see my slide. Okay. So lambda function is a one-liner. It looks like this without the return, but this is the return value. Or it looks like this with a condition. And again, no return, no colon. All right, be careful. So the normal function looks like this with a def. The function that we want to use in all this stuff is with just lambda, without the return. Okay, so for I should show you 2. Let me just comment out this guy. All right, for today, let me just give you another. I need to get up my code. Okay, yeah. So you can write things like this. All right. So when you say A 100, it means that X is 100. So X comes in 100 greater than 10, correct? So you get 10. Okay. And you can write A minus 100. Minus 100 is not larger than 10, so you get 0. Okay. And you cannot, this one is wrong because the if statement should be in between here. Okay. And you cannot have colon. Okay. Cannot have colon. All right. So B is not allowed. On the other hand, you can do things like this. You can have a X. If X is larger than 10, you output 10. If otherwise you output this thing. You see, you can cascade a lambda into lambda, right? So this is a lot. So when you say C100, you get 10 because X is 100 greater than 10, so you get 10. If you say C minus 100, you will get a function because minus 100 is not larger than 10. Therefore, you output this guy. So this C100 is actually a function. So if you want, you can see that this 100, you can pass in the parameter 12 because it's 12 is the y. So y plus 1 is 13. So you get 13. Okay, so cascading a function lambda is possible. Now, for today, we are studying two functions, the sum and the fold. How do they look like? All right, in the case of sum, the function is here, which is here. It's that when you pass something, you can see that this term is actually a function because you apply on a value. You know that A is a value because A greater than B, there's plainly A and B are two numbers. Okay. And next is applying to A, so you can see that next is actually another function. And so this routine is doing A, or it's trying to do until A is no longer larger than B, and A's value is changed because of this recursion. The next A, so A, the next value will become next A, the next value will be next A. So it looks like this. Originally, you get, when you first comes in, you have term A plus sum, the term, the next A, and next, and a B, which is this line. All right. So the term A, it's a function applying to A. You get some value. This value wanted to add with the back, but the back is a function, it's not a value. So you have to expand this again. Expanding this will give you term next A plus sum term next A, next B, and so on. So these things keep going on. It get expanded from next A to next A to next A until all the way to near to B. All right, which is this one. And once it's expanded, then you got reverse back to get to your the sum up of this thing. So because addition is associative, so summing it this way versus summing it from the back is going to give you the same answer. By the logic, you are supposed to sum it from the back to the front. Okay, but as you will see in the last question, you'll be hard to sum from the back to the front because you needed to know what is the last value of A before it exceeded B. That will be the last guy that you have to take and add it to the front. That will be hard unless you want to use a list to keep track of the value, which we don't want to. So you are allowed to do sum of this way because summation is associative. On the other hand, for fold, it looks like this. The structure looks similar, except that this term A, it's now become Fn. All right, term A is Fn. The op here is the substitute for the plus. So this op could be any function. It could be an add, it could be a subtract, it could be a divide, it could be a whatever you apply. It could be a factorial also, possibly, right? So whatever it is now, the associativity is gone. All right, so you have to be very careful. We are no longer talking about, you're talking about this value added with operator on this other guy. So swapping the two will give you different answers. So you have to be very careful. So what does this do? This is doing op fn and expanded out become fold op fn minus 1. So this function is giving a value, but this fold is a function, so you needed to expand it out. You will get this expanded out will be op this fn minus 1 and fold another type. And then you can see that this green bracket and this green bracket will have to be done first. The result of it is going to be work under this operator with Fn, right, and so on. So the expansion is from n all the way until 0, okay? And then you have to fold back one at a time until the beginning. In this case, you really must do it from the back to the front, because you are not sure op is it associative or not. All right. So between sum and full, actually there could be difference. First of all, sum is using things that sum is jumping around with the next A, need not be by one at a time. On the other hand, full it's always from n to n minus 1 to n minus 2 and so on. So this is decrementing for sure. This is incrementing, but its incrementation is not necessarily by 1. It's by the next A. Okay, so this is one difference. Other difference include also this is a plus, so it's associative. You can anyhow from the back or back to the front. But op, you cannot do that because you're not sure. All right, so op looks like this. And I should give you this. The op, it looks all right. So the calculation is that the first number you calculated is F0, because the last guy, just now you saw, the last guy is F0. This F0 has to be worked with F1 because it's op F1, F0. The result of it is called RES. This RES is then worked with F2. And the positioning is important. This F2 is on the left, the result is on the right. All right, then you get this result 1. This result 1 is on the right again, work with F3 to get result 2, and so on. Okay, so this you have to take note. But all in all, you're not supposed to remember or memorize this definition. In our assessment, we can change all this. We can use sum for different purposes. Need not be, just like you saw, it need not be the system sum. It can be my sum. And actually, you will follow, if you take a look at the midterm set by me, yeah, it's a new sum. It looks something like that. I could have called it sum also, actually. You can have other, I call it sum t, but it can be, I can actually be nasty and call it sum also. I can have many other example. This is sum t also. Are they the same paper? 21, 22, 20. Okay. All right. So take note that recitation 3 is a simpler version of our midterm in the sense that recitation number 3 works with numbers. Okay. All my midterm here, it is not working on numbers. It's working on tuple. This is a tuple. This is a tuple. All right. So tuple is harder to work with because it's a collections of numbers, not just simply a number. Okay. So when you try out this, which is in a month plus a few days times, you should try out some of this paper because they were set by me. Okay, so these are the two notes. Okay, if you have no question, give me a check and then we can go into all the problems. Yeah, okay? Okay. All right, so let's go into the problem. So the first question, this one. Let me keep this. Okay, question 1A. It looks like this. Question 1A. All right. Okay, Let me try. Yang Yichen.
Yeah.
Hi. What is the answer for this?
Is it 17?
17. How do you get 17?
Cause y is 10 plus 5.
Y is 10 plus 5. Oh, X is 5, so Y is 5 plus 5, so it's
Oh
10.
yeah, I mean a function f is 10 plus 5.
Okay. Sorry.
Then x is the global x, so it's 2.
Okay, so this 17. Let's run it. Okay, 17. Okay, now if I change this to below, oh, come this guy. Okay, what will be the answer now? Yichen.
14.
How do you get 14?
Cause y is 2 plus 5. Then you return 2 plus 7, so it's no,
Is
you return 7 plus 5, so it's 12 for your function f. Then plus global x, which is 2, so you get
Okay, your reasoning is reasonable, okay, but you are wrong. All right, because the Python interpreter takes this whole thing and realize that there's an X here, okay, and there's an X here. These two are the same X. All right. Since they are the same X, you cannot use the X without giving him a number, giving him a value. All right. Let me say that again. Your reasoning is reasonable, but it is wrong in the way that Python interpreter look at it. Python interpreter sees this as a function. As it is a function, if you tell me this x, it's somebody you want to work with, then this x and this x are the same. But the moment that you hit here, you don't have a value for this x. Therefore, you have an error. Okay? X where it is not associated with a value. Is that okay for you?
yes.
Okay. All right. So this is something peculiar, it against your logic, but it is what it is. It is how the Python interpreter see the whole thing first as a function. So as a function, you must give me a value, all right, before you use it. Okay. Now, if you remove this, what do you think it is now? Yichen?
Is it an error?
No, this time no error.
So I can
This
use
is
a global x.
yes. Now you can use a global x. Why? Because there is no conflict about x. X is not being assigned a value, right? So this x is now not the local guy, but the global guy. Okay, this is what I wrote down here. Forgiveness attitude. Or I don't know what is the better word for this, but forgiveness is what Python interpreter can do, right? If a variable is not on the right hand side, all right, this is the left side. Just now the x, if you put the x there, it's on the right hand side. It can be obtained from the global. Otherwise, one need to declare its global to be used. Okay, so let's run this to prove the point. All right, now it's 11. Why? Because f empty goes in x it's considered as 2. So this is 2 plus 5. This is 7. 7 plus 2 give you 9. So this is 9. 9 plus 2 give you 11. Okay. So this is what is the answer is the same as if you put global X. All right, it's 11. Now, if you have just now the case X equal to 5, you put there. Now, this X, because of this keyword, it is now global. So this whole program will still run. And then the answer will be this global X. So this is 2. 2 plus 5 is 7. But the global X is now 5. So this is 5 plus 7. So they give you 12. 12 plus this X is no longer 2 because it has been modified to 5. 12 plus 5 will give you 17. Okay. You got it, each one.
Yes.
Okay, good. All right. Yeah, so that it's question 1, the forgiveness attitude that you should watch out. Okay, let's try B. Okay, B. This might be. Oh, here. Y is equal to X plus 5. X is equal to 7. Return X plus 1. And I want to print GY plus Y. Okay, let's try Godwin. Leonard.
Yes, bro.
Hi. Okay, what is this answer?
The output will be 18.
18. Let's try. 18. Okay, you're correct. Let's go through. GY, it's G3. So X is 3. So 3 plus 5 give me 8. And X is now set to 7. 7 plus 8, 15. 15 plus 3, 18. Okay, that's correct. Now, we were trying out just now. So let's say if I put global X, what do you think that will happen?
Y will become 2 plus 5, so Y is now 7. Then X will be set, global X will be set to 7. 7 plus 7 becomes 14. So GY, which is 14, plus Y, which is 3, will become 17. Final answer 17.
Okay, so you go very fast. But you are wrong now. This global X is not allowed because this X is a parameter. You cannot set it to be global anymore. Okay, let's run. Name X is parameter and global. It doesn't allow you to. Okay, so this is error. Can they accept that? Once again, this is the same as just now, this is the interpretation by the interpreter, and we have to respect it. Okay, so this is a mistake.
Okay, can prof.
What about this? Godwin.
In this case, I will assume it will be like the reasoning which I explained before. So we will now use global Y. Y will be set to wait.
Okay, slowly.
Yeah, a bit
So
confused.
this X is what? X is equal to
3.
3. And global Y means Y is equal to
3.
3. And what is this guy doing? This guy is 3 plus 5. Y is equal to 8. All right. This guy is 7. And what is this guy? This is 7 plus 8 is 15, right?
Yep.
15. And so this is G3, which is 15. And Y is equal to what?
I believe they're setting it to 8 since we're using the
Yes.
whole Y.
Yeah, correct. So it's 15 plus 8, which is 23. Okay, 23. Okay. All right, so next 1C, which is this. This should be easy because blocking is already so much difficult, but this should be easy. Let's try Lim Chi He, Chen He Lim. Chen He Lim, is it?
Hello?
Yeah.
Yes.
Yes. What is the answer?
Question 1C for me, I got 4.
4. Why?
1C. So the global x is 4. Function full x will take x and return x3. So the x, I'll presume that you're taking a function because the return is a x, then a parameter 3. So full lambda x will give you the function x plus 1. So the lambda x and x plus 1 is the function. So when you put it in, the new x in the lambda x will be 3. So 3 plus 1 is 4.
Okay, you're right. Right, is 4. So that is to say that this x and this x has nothing to do with each other.
Correct.
This x, you can ignore him.
Yes.
You can just still get 4. Okay, good. 1T. Oh, is another easy one. X equal to 5. Okay. Lim Jun Kai.
Yes, Prof.
Hi.
I evaluated it to 16 because for uh since x is in this bar for and then y is lambda x squared, then the global variable x of 5 doesn't matter, so it's you put four squared, and then that gives 16.
Yeah, that's good. Let's run it. Let's give you 16. That's correct. So this global is useless, as you say. And you are correct. Okay, good. All right, so the lessons here is basically understanding that the forgiveness attitude that Python has, and also to note that it is global or not global. All right, so that's all for this part of the exercise. One thing I should say this more often is that you are encouraged to do or to questions us, in a sense that you see something but you can play with it, you can question what will happen what if this thing is moved around and so on. This is also how we examiners set questions to test you. Of course, every year I have to come up with new questions, and I always have to revise what has been said before, and what are the things that students usually make mistakes. And we try to catch some of this, and if you're not careful enough, and so that you should learn from all these things. Okay, so have the attitude of asking questions yourself. Then if you can't solve it, you can always check with your TAs, or you can always post it in the forum, as a new question, nobody will question you in the sense that we encourage all the discussion in the forum. All right, as long as you're not posting solutions to our missions, then you are okay. All right, now back to question number 2. Now we are going to write my sum that compute the sum for n greater than. So you can see the pattern 1 times 2 plus 2 times 3 plus all the way until n times n plus 1. So I needed your help to post your attempt in our chat box, and then I can pull it up and for our discussion. All right, try. Put it into the chat box for question number 2. Okay. All right, already see some iterative solution. Yeah. Any more? Okay. Interesting. Okay. So the tricky thing here is that you want to know, oh, this some lambda. All right, so Davros, you are already using the sum function. Okay. If you write yourself, so this is how it looks like. I just pull out mine, it's the same as yours. It looks like this. The main thing to be careful is that you want to stop at the right place. All right. For example, here, when n at the last n, it's actually the last n times the n plus 1. So the recursion should be the last n is the n times n plus 1, followed by chopping him off until the n minus 1. Okay, so this is the nth term, and this is the terms that taking care of from 1 to n minus 1. So let's run this. All right, it's 440. Okay, so if you're not careful, then you may lose one term. All right, for example, so if you not careful, for example, you will use this as n times n minus 1, then you will lose one terms. All right, you will get 332 only. So it's this should be a plus. All right, and also the base case is when you have one term, so you must have the 2, 1 times 2, so you return 2. Okay, so this is what you have. All of you are pretty much doing this with we are going to see a iterative process. So let's see if most of us do this as a recursion. So we can do an iterative one. Can I see your posting on the iterative one? Already there's one, but we can do, I can still take some more and take a look. Okay, yeah. Wang Xihen. Okay. Okay, so there's not much difficult, and here's what you have. Okay, so this is question 4. Question 3 is the time complexity. We'll come to that shortly. My sum. So let's see, we get the same answer. 440 for the previous version, recursion. This is a 440 for the iterative version. Okay. All right. Recursive is 440, iterative is also 440, so we are correct. Now, back to question number 3. So what is the time and space complexity? Let's take a look at number 2 first. So what is the time and space complexity for this case? Can you type it out? Let's take a look. What should be the time and space complexity? Nobody tell me. Oh, okay. Godwin Leonard tell me that is ON. All right. Both ON, yes. All right, so this is time is ON Y, where N is the input number. Okay. Space is ON Y, where N is the okay. So because there's a plus and it has to be deferred. This guy has to be, if you go into Python tutor, you will see that this is actually stacked onto the system stack or deferred, and you have to get this number first. So you are actually doing this recursion with this, but this value must wait until you hit 1 times 2, the base case to get 2. Then the 2 has to add it with 6 and add it with 12 and so on. Okay, so the space is ON because you have deferred n of them. As for the time, of course, this is a recursion. Each time you reduce the n by 1 until you hit n equal to 1. So the number of times this is happening is ON. All right, but one thing to note here is also that I just see this sum is actually not really this sum. This sum is the opposite. So if you want you to be more correct, it's my sum n minus 1 plus that. And this is a more correct version to respect the summation is from the front to the back. Okay, you still get the same answer, just that the semantically, this one more following this guy. Okay, this n times n plus 1 is at the back. It's at the back, whereas this guy is in the front. Okay, but there's still an issue with who is more efficient, but I will leave it to you to find out about tail recursion. Okay, so this is time is ON and space is ON. As for the iterative looks like this. This is, you only need this variable and you return this variable, and you need this I. Also, you need this range. So you need 3 items, sum, I, and this range object. So these 3 things is constant. So the space is constant, O1. As for the time, this is still looping for n times. So the time and space or the iterative, its space is O1. There's nothing to talk about. Okay, so for iterative question 4, it looks like time is ON, but space is. One thing to note always is that don't make this mistake of the time, the space can never be larger than the time. So it can only be smaller, right? Because if the space is n squared, for example, that means that you are using up n squared space. You better have the time to use that space. All right. So that this kind of scenario is not possible. Okay, because the time is less than the space. This never happened. Okay, it's only the other way around. time is always no less than the space. Okay, so this is just a side note that you should always remember. Okay, so we are done with 2, 3, 4. Number 5. This is a standard question in midterm. So you can see, right, T1, T2. What do you put? You see all the lambda. Lambda again. Lambda again. All right. You see the lambda doesn't have a return, but it's something add up and raised to the power something's from the end to the beginning. Drop the first guy. Lambda with the if condition and so on. Everything is lambda. Okay. Same for the other. You see lambda, lambda. You see lambda, lambda. Okay, so lambda is something you cannot run away from. Okay, so we can also define my sum in terms of higher order function sum, which I saw just now. But let's see again. So my sum is this. So can I see your posting? What is T1, T2, T3, T4? Okay, let's see. Okay. All right. All right. Then I see. So now I see. All of you have the same answer actually. Except that you should question yourself. Hey, can there be another answer or not? I'm asking you now. Is what you have the only answer? What you have is this. Let me just pull it out. All right, you have this. Pretty much all of you have this. I don't see any difference. Okay, my question is, can you do something different? All right, 440, you're correct. Yes. Question is, can you do something different? Okay, so actually you should be able to. Here is a trick that I can play. My T1, I don't want this. Remember just now I show you, I could, instead of thinking about this 1, if I think of this 2, okay, that means it's my 2, I start with 2, and I end with n plus 1. Okay, so if I start with 2, I end with n plus 1. Okay, but my function become 2 minus 1. So this is minus 1. Okay, let's try. And my increment still remains the same. Basically, I still from 2 to 3 and so on. So this is no change. This is change. This is change. This is change. Let's see. I still get 440. All right. So you can challenge yourself. Actually, there are many, many answers. Actually, there are infinite number of answers. So here is another one. K equal to 4. If you allow me to add a parameter, I can change this to x minus k. Then this one is x minus k minus 1 plus 1. And this is my k. And this is my, the ending is n plus k. Okay. I still get 440. If I change this to whatever it is, I still get 440. All right. So you see that same sentence like this, you can interpret it at least the two convenient way. You start with 1, then 2, and you end with n. Or you start with 2, then 3, and end with n plus 1. Okay, so there are already two ways. And another third way is you start with somewhere the k, but you subtract it away. All right, and again, these two are differ by 1. You multiply them, and that is where you start, which is the k, and you end with n plus k, and no change to the increment. You still get an answer. All right, so don't you should be able to see this thing, because once you know how to play with this, then you will be able to think more about how we can play to get, for example, prefix sum. Actually, they are quite interesting, interleaving, right? Which is you take this tuple, you're trying to interleave with this other tuple to give you 1A, 2B, 3C, right? You can have 1, 2, 3, 4, A, B, C, D, or even A, B, C, something else. Interleave, take a 1, take the A, take the 2, take the B, take the 3, take the C, and take the 4, and take the another 1, 2. All right, so you need to, these are more harder in the sense that they are dealing with tuple. Okay, that is question 5. Question 6. Now you are supposed to use 4. So let's see your 4. Okay, can you post your 4 for me to see? All right, you can ask yourself, can you have an alternative answer? All right, which you should be able to realize that now. All right, for those of you who have already posted the answer, you can post another alternative answer. Lambda k accumulate. ACC plus k times k plus 1 is O 0n. All right, so this one I'm not so sure. Let's try. Oh, why is it so? Okay, what is this one? Okay, let's try this. Okay, let's try this. Okay, so this is wrong. Okay. All right, so this is wrong. So this 资源菜资源. This is not right. Okay, so I see most of your answer looks like this. It looks like this. Okay, so let's try. Okay, so it's correct. It's 440. Again, the same. that you saw the interpretation of the sum as 1 times something, 2 times something, until n times something. Once again, you can think of it as 2 times something first, then 3 times something, and so on. So I can modify this guy to become x plus y lambda x. I will start from x plus 1 and x plus 2, and then I reach n at n minus 1. Let's see this guy. All right, I still get the same answer. Okay, so the interpretation allows to be like this. You get the same thing. Okay. Yeah, we forgot to think a little bit about what will be the time complexity here. Okay, maybe we can do that at question number 7. Okay, question number 7. All right, 6, I am giving you a different alternative that it still work the same. Now you're supposed to write an iterative version of the sum. So can you do that for me? All right, the sum looks like what you saw. Okay, yeah. Mm-hmm. Okay. This Sun Si your thing has some problem to me. For I in range A, comma B plus 1. You know what that means? That means that you are taking I from A, then and then A plus 1, A plus 2, and so on. And in that way, but your I is not used. So you're also in trouble at some point because the next A is going to get you lots of numbers. So what you wrote there should be wrong. Chai Ziyuan, what you wrote down here, it's not iterative. Okay, Sun Siyan you change, but still wrong. Siyuan, are you there?
Yes, Prof.
Yeah. Did you get what I meant?
Um,
Okay, so you are using a for loop. A for loop with a range will then be A plus 1, A plus 2, A plus 3 until B, correct?
yes.
But your next A, it's not going to respect that. Next A can be jumping by 2 steps. The next is a function that you do not know. You get what I mean?
Understand, Prof.
Yeah. Okay, so what you wrote down there is wrong. Okay, so most of the others should be okay because you can use a while loop. A while loop should serve the purpose. Okay, it looks like this. Okay. You take the total to be 0 and then you do the term A to give you the function and you next. Because this next A, the A here doesn't mean that it necessarily be plus 1. It's only for our example here, it's plus 1. In this case, it's a plus 1, plus 1, plus 1. But as a function, sum, it need not be plus 1 all the time because it's the next A. Otherwise, you can just simply put plus 1. Next, allows you to change whatever. You want to jump 2 steps also can. You want to jump 3 steps also can. All right, so actually, just now the one possibility to make it correct is with the for loop on the range with from A to B, comma, next A, and that kind of thing, then can be more closest to it, but I'm not so sure it's the correct amount. But this is the correct one. So it looks like this. The total is 0. You do it when A is always less than B. All right. When A greater than B, you return 0 already. Okay. So you do it when A is less than or equal to B. The total is the original total from 0, starting from 0 plus whatever you work on it, added to the total. Then A become the next A. And you finish. Then you return. Yes, Lim Chen He, you have a question?
Hello, Prof. I'm
Yeah.
just wondering, because for me, I did it a bit differently. My result wasn't, I didn't equate my total to 0. I equate my result to the last term, term B. Do you think it'll work the same, or will
Can
it
you
like differ?
post your
Yes, okay.
okay. All right, so let's see. Result equal to term B. Wrong for sure. Term B, it's applying to B. Okay, you are applying it to B, but you can't tell A can reach B.
Okay.
All right, this is the case that it could be it's something like this A is equal to 100. Next A, it's equal to A plus 2. Okay, and
Okay.
B is, let's say, I should write it this way. Next A is equal to A plus 2. All right, so A is starting from 1, 3, 5, right?
Yes.
7, right? All the odd number until maybe 99. Okay, and B, I make it a bad guy, is 100.
Okay.
So you never reach B.
Okay.
So you never apply term to B.
Oh.
You at most do until 99.
Mm.
Okay, so you got it. Yes.
So with my solution, I will add the 100, which is not supposed to be added, because for this sequence is a odd number.
Correct.
Okay, Ken. Thank you, Prof.
This is the same problem with just now, this Sun Siyuan. You can't be sure that you are reaching the B. In this case, for I in range A comma B plus 1, you're always going to reach B, but B is never a definite thing for you.
Mm.
Okay?
Yes, understand. Thank you.
So, welcome. Let's try to get the answer and see it's correct. Okay, let's run this. We regard position A next B. Oh, sorry. Oh, I have to do the same. My sum it's lambda. I have to do the lambda thing. Lambda. Let me cheat by copying. Where's my sum? My sum is here. Oh, okay. I know where to copy. Okay. Lambda x times x plus 1. And then I start from 1, and lambda x plus 1, and I end at my 100. or 10 in this case. Yeah. Oh, this is the explicit use of this guy. Anyway, it works. Okay, 440. I shouldn't be cheating like that. I should be using some iterate. Okay. Should be doing this. Give me a minute. I should be doing this, and here is my sum iterate. And then I can bring my sum to 10. Okay, that's what I meant. Okay, this should be the use of this guy. It means this. Okay, 440. Okay. So now we have a chance to take a look at what is the time complexity, which I did make a mistake yesterday. It was pointed out by one of you. Okay, so what is the time complexity here? Let's try. Brandon, is it? Brennan. Yes. Hello, cannot hear you. Is your mic okay? Okay, cannot hear you. Brian Bay. Hello. Brian, yeah, your mic is on. No, no sound. Okay, anyone want to try? Okay, Jordan. Jordan. Oh, sorry, Yang. You have something to say? I can't hear you. Is it some problem with the mic now? Can you hear me? Hello? Yeah, you can hear me. Oh, but I cannot hear you. Okay, Godwin.
Yes, bro.
Oh, I can hear you. Okay, so what is the time complexity of this guy?
Time should be O n, where n is the input of A.
Where n is the input of A? No lah, you are too awkward, huh?
Yeah.
It's not quite. Let's try. There's no n in here. Okay, so don't use n. What do you see? You see that A keep changing, right? So you got A equal to 1, 3, 5, 7, and so on, depending on what this next is. All right, but ultimately it's going to be from A until B, right? So it's something like A is something like B minus A, okay, and it's something like this that divided by next, all right, depending on how next changes. Okay, so this is the number of times. All right, so this is one term. This is one item. This is the number of round that you need to go through here. And this has to be multiplied with the actual effort. What's the actual effort? The effort is this checking, this addition, and this function. This function usually is an easy function, so this could be a constant time. So the tricky thing is this term. Okay, depending on what is this term, so times the time taken to do term. All right. Okay. So, Godwin, are you with me?
Yes, prof.
Okay. And then what about the space? The space, this is a constant. This is a this is constant. This is given. This is given, and this is a plus. This guy is a function. So depending on what is inside here, usually this is a constant, right? It's simply lambda x plus one, that kind of thing. But the tricky one is this term. All right, so the space is O1 or the max of O1 with the rest. So it's O of the term A or term B. Or we call it the max. I can put a max. Usually the term, the last A. Okay. I would think that the term last A is the one that is usually the largest number, so it should be the largest than the rest. So maybe I can ignore all these things and put it as such. Is it okay? Godwin.
Actually, prof, can I ask, in this case, if you know that the term is some very simple function, would it be a constant? Would the space be a
Yeah.
constant?
Yes, yes, yes. But you can imagine, the term can be a factorial, a recursive factorial,
Okay.
and which we know that the space is ON, correct?
Yeah, can, prof.
Okay. Yeah, so that is the time and space complexity for this guy, which I didn't do well yesterday. All right, now we are at number 7. We need to do one for number 8. 4. Can I see your 4? Number 8. Okay, number 7, it's easy in the sense there is an addition. So there's no issue with you add A plus B or B plus A. All right, because it's associative. But be careful with number 8. Because number 8, it's 4. 4 is working on one or the other way. You will get different answers. Okay, I see mostly correct. But Darius, you cannot add with I equal to n, you add total equal to 0 plus. Oh, okay lah. The last guy you initialize basically. Okay, so it's a little bit awkward, but it means that. Okay. Okay. Cleaner one I'm seeing now. All right, so it's not that difficult. It's quite easy. Let's see. Okay, here. All right, it looks like this one. All right, so it's simply I'm using a while loop. Some of you use the for loop. In using while loop, I have to add one myself to go to the next guy. And you see that I'm careful. I take my F on this side. If you not careful, you use this and then you will be wrong. Okay. RES is the result, which I use my PPT just now. See the RES, the result. Okay. So this is the routine. my current is 1 because I've done my 0. So I'm doing my 1 and then my 2 and so on. So this is my 4. Okay, I need to copy my 4. I'm using my 4. Where was my 4? Okay, I messed up. So let me copy it. Just give me a minute. Okay. My 4 was here. Okay, my sum 3, I use my 4, this, and I print my sum 3, 10. Okay, let's see. Three, 4, 4, 4, 0. Okay. So that's not the end of the story, because if I use this, if I comment out this, I use this, I still get the same answer. All right, but this answer is wrong because this guy doesn't respect the the associativity. Let's see, how do we check? We can do a change of this guy to minus, and we call the same function. We call the same function our original, original 4. I should get, this is my real answer. Okay, this is my another iterative answer, which is a wrong one. Why I can, because, okay, let me comment out this guy first so that there's no dispute. All right, so if I do a minus, I should get something which is not 440 anymore. All right, I got 60. So now this is a 4 original one. All right, original 4. Now I created my own 4. I would expect I also get 60, right? But it's not the case. I get minus 440 because I make a mistake in this line. So now you can uncomment this, comment this. Now I get the same answer because I respect the non-associativity. Okay, so this is how you have to test it. With one example, you get an answer, doesn't mean you're correct because you're not respecting the associativity. Here, there's no associativity, so you have to be rigid in doing this versus this, which is wrong. All right, you can try other example. Let's say divide. You should expect the same answer. All right, but the tricky thing for divide is that you may divide by 0, so you better plus 1. All right, then here also plus 1. All right, so you're never divisible by 0, and you should get the answer the same. All right, 10.0, 10.0. So if you make a mistake like this, you will get a different answer. Okay, one get 10, the other one gets 0. All right, so this is to ascertain what you get is what you wanted, respecting the order of execution. Okay, I'm done with number 8, and there's no more. All right, any question? Any question? If no, give me a check. We can go home. You can Happy New Year and Happy Valentine's Day if you still in time. You still have a few hours.
Actually, I have like a question. Sure, it's like
Go
not
ahead.
a very smart question, but okay. But since like we are going to defining like ops and like next and like term all of these ourselves, like why if we just switch, like let's say we use instead of op to like combine the terms, let's say what if we use like term instead, or instead of using next to iterate to the next term in the next
here,
op.
are you talking about for?
Yes, like for and like
Okay, let me
just
pull
in
out my slide.
general.
Okay. All right, you see that sum and for, they are of difference in the sense that for has only 3 parameters. All right. Of course, I can create 4 parameters. I can add a comma. For example, you're asking me in my midterm, I could just create a for that will jump around with a next in there. That is possible. Okay. That will be a different for lah. All right. For here, this guy, if I have a next here, I would mean that I no longer take n minus 1. I will have to put the next, maybe I'll write it out. Let's take our original for. Original for is here. Okay, here. So you're talking about taking a next, okay, as a function. In that case, I will change this to, oh, there's a tricky thing here. Next. So next n minus 1. Sorry, next n and next. So it looks like this. Okay. It still work, but it become tricky because this next would have to somehow make sure that your n at the end is 0. Then it can stop. Maybe in that case, you would have to change this to greater than 0. Then the moment that it reaches 0 or below 0, you can stop. So this function may still work. You see where I'm trying to get at? By allowing you to play with it, you can indeed change. For example, you see my question. This sum has only 3 terms instead of 4. Okay, it has a next, it has a term, it has a t for tuple. All right, it doesn't have a a and a b anymore. So it's possible. It's serving another other kind of use case. So the input is tuple 1, 2, 3, 4, 5. Okay, and it doesn't add all the numbers together, but it add alternate number 1 plus 3 plus 5. It's a 1, 2, 3, 4, 5, 6. You also do 1 plus 3 plus 5. You skip 2, 4, 6. All right. So it depends on your purpose, and you can, of course, modify it for whatever you want. But be careful. Terminating condition must always happen. Otherwise, this thing will go into an infinite loop. Other than this, I think you are free to anyhow do things. Yeah. Yeah. Does it answer you?
Okay, can, yeah.
Okay. Or you can ask more specifically. Otherwise, that will be my answer. Okay, next question. Okay, Lim Chen He. Yes, go ahead.
Hello, Prof. Can
Yes.
I check with you, right? What's the difference between a sum for like the main difference is like for sum, right? The operator is always is locked to the plus sign, right? Then for whereas for fold, the operator can like change to multiply and plus freely. Then my question to you is, right, if let's say I want to do a fold, right, can I do a fold for terms like for a sequence of odd numbers? Let's say a sum or multiplication for odd numbers.
Ah, okay, you can. Let's try.
Yeah, because I realized the for the fold you put in the PDF, right? The next term is fixed to n minus one, n minus one, n minus one. So it's only you can jump by one term down, one number
Right.
down. Yeah.
Correct. Yeah, correct. Yes, you're right. Just now I attempted to put the next here. Then I will be able to change not just by one, but by whatever I want to.
I see.
And then in that case, okay, let's play with this in 10 minutes. Okay, let's see. If I do for F and this will be next I and the next one will be next. Okay, let's copy this to another file because the rest will give me error. Okay, you want to or let's say you want to do
Multiplication of odd numbers.
for okay odd number,
Yeah.
if I sum of okay and for example
Yes.
1 plus 2 plus 3 and so on, right? So what do
Yes.
we do? We'll return 4 and our op will be lambda
The x,
x
y.
y x plus y, and then our function is just return itself, right? X is x. Or I can play cheat if x is okay. Return x if x divided by 2 is 0. So it's 1. That means that it's
One
odd,
remainder. Yeah.
else I return 0. Then my next is still the same thing. So once I play this cheat, my
Yeah.
next is simply lambda. Let's play this x minus 1. That's the
Okay.
next one. Then the next, oh, sorry. This is n. And then my lambda, it's x is x minus 1. Okay. This should give me one answer. We can see another one afterward. Print sum of to let's say 10. So 1 plus 2 plus 1 plus 3 plus. Let's see how. I may have to modify a little bit. Okay, it's 0. So something is wrong. To 10. If n greater than 0, f0. F is a function. The function is here. So if I return x, let's see what I get. Get 0. 10. This is 10. Operation is this. Function is this function. A. Okay. I'm under stress test. N minus 1. So let's sum it out first. What do we have for sum? Let's try this first. Can you help me to check why do I get 0 always?
Yes. Checking.
Huh? F0 is my op. This is my F. This is my N. Okay. This is how I play.
I think you put the if n more than 0, then return f0. So your n is 10, you always return f0. The fold function at the second line.
Full function second line, return F0. Oh,
So
I'm sorry.
yeah.
This is equal. Okay. I got 55, which is correct. Okay, so now I need to make sure that I don't add the odd number. So if it is, I don't add the even number. So if it is odd, then if x divided by 2 equal to 1, then I have it L0. Okay, I do this. I got 25.
Yes, correct.
Correct.
Yeah.
Make a smaller number, 5. Okay. I got 9. So I don't need this screen anymore.
Yes.
Okay. And now I want to play another game. So I want to do a next. Okay. Here will be my next function on n. And I have the next function. Now I don't need to do my if statement anymore because I take whatever I have. My next is going to tell me, but I need to define the next, which is my lambda. X is x minus 2. So I step down. So if I start with 5, it will be 5,
Yes.
3, 2, 1. So this should be correct. That maximum recursion, because this is can never be equal to 0, it's less than 0.
Okay.
Less than 0, I should return 0. Okay, it's
Okay.
9. Then let's try
6.
10.
Okay.
Or 8 will be trouble,
Yes,
because
because it's even. Yeah.
even. Okay, but that means I'm adding even.
Yes.
Okay, I get even 20 with
Yeah.
8. Why? Because it's just 2 plus 4.
Yeah. So this should be
plus-
somewhat even numbers.
Okay, so this is correct. Okay, so you see that just now, to answer you as well as just now, the other student, I can play with next, and I can actually jump by more than 1.
Yes.
Otherwise, I will have to change my function here to take a if statement. All right. So these are the flexibility that you have to play with to get to what you want. Okay. Yeah. By trying out some of my paper, you will be able to see that, wow, things are actually very flexible.
Yes.
Yeah. All right. So you can actually take this kind of thing. You can fold it, raise to the power of 2, and so on. Yeah.
Okay.
Okay. Thank you for the question.
Thank you so much, Prof.
Okay.
Sorry, I just wanted to ask another question.
Yes,
If
go ahead.
use the fold with the next, right? And the
Yeah.
fold without the next, is there going to be any difference in the time and space complexity?
Okay. Yeah. It's going to end up like what we talked about just now. Here. question 7, when we were working on some iteration, it became that something has to be deal with the next. We cannot run away from it. Yes, the number of times that you needed to go through the loop, it's now changed.
So what will be the time complexity for this? Or
Ah,
with the
okay, I would accept this kind of stuff. In this case will be, you can say that, okay, let's put it in. If the time should be something like you started with n, then next, so it should be n minus 0, which is n, right? Because it's less than 0, divided by next in some form. So I meant that times the time that you do the function, or the time max of time for the function and the op, right? Whichever is higher. Then n divided by next, I meant that n, next n, next n, the number of times that we apply next to n to reach n less than or equal less than 0. That's what I meant. Is that okay? Well, it comes to the point that we cannot have a clean formula to describe what we want. We can accept description like this.
Understood. Right.
Okay?
Thank you.
Okay. I'm thinking of posting the question to the forum to ask. I will do that about syntax and semantic, similar to this kind of stuff that you have done your mission actually. I'll post it. All right, anything else? Yeah, okay. Okay. Give me a check and then you can go. Okay, bye-bye. Happy New Year. Okay, I stopped the recording and I stopped the session.